Greetings, AP students. We're going to be working with a few final gas laws today. We're also going to throw in a little bit of stoichiometry, so you'll need some note-making materials and definitely a calculator to work with. Again, I'm starting this unit, even though it's AP and this should be review, we're going to assume that you've never done any of this in pre-AP. I'd rather start with that and work our way forward from there. So I hope you have seen this before. If you have, it's likely it's been a good 9 months, maybe less, maybe more since you've seen it. You're good for a review anyway. So consider this a really great review, or if it's brand new, consider it brand new material. And it's easy, but there's a lot to keep track of. So don't hesitate to pause the video and catch up in your notes as we move along. Okay, I want to start off with Graham's law, sometimes referred to as Graham's law of diffusion or effusion, and often on the AP test, they will use the words diffusion, effusion, and not even mention Graham's law. And that's okay, because here's Graham's law. Graham's law says the rate at which gas molecules move is inversely proportional to the square root of their molar masses. It's that easy, right? Yeah, okay. Chill. First off, I cannot imagine you would ever need to calculate this. So that is the formula, that's official. However, it's not on the formula chart for the AP chemistry test, so I don't think you'd have to calculate this. What you do need to know is the answer to this very simple question. What is easier to move faster, something heavy or something light? That's all there is to Graham's law. If you can answer that question, then you know Graham's law. So you already know Graham's law. Great. Now I'm going to show you how this works out with numbers just because. I don't think you would ever need to calculate this on the AP exam. I cannot foresee that being a thing because it's not on the AP formula chart. But we're going to compare oxygen to hydrogen. Okay, I'm going to look at the rates at which they move. So let me get something to annotate here with. Yellow should work just fine. Hope you enjoy the background and the fancy writing because I was feeling fancy today. And so we have a fancy background and some fancy writing going on today. Don't expect me to continue the fancy writing. That's not going to happen. Sorry. Okay, so I need their molar masses. Well, I picked oxygen and hydrogen because those are like super fast, simple. We're going to call hydrogen 2 and oxygen 32. Okay. It really doesn't matter which one you call which here. We're going to analyze the results either way. So I'm going to do both. What if in trial number 1, I call oxygen M2 and hydrogen M1? So I have 32 divided by 2 and then square root it. I would see my rate is equal to, okay, 32 divided by 2 is 16 square root 4. Okay, what's that mean? Well, we're going to get to that in just a moment. Let's flip it. Okay, so 2 divided by 32 square root. Okay, well, I'm actually going to simplify this first. Let's call this 1/16. So now you can see it simplifies and square roots then into the rate is 1/4. Now, first off, notice how our answers relate. They're inverses because that's the only thing that's going to change. What do these numbers mean? What's going to move faster? Something light or something heavy? Something light, right? Yeah, you got it. You're smart. So what's this saying is my hydrogen's going to move 4 times faster than the oxygen. It's 16 times lighter, but it's only going to move 4 times faster. Now that's Graham's law. He did the experiments to prove that it's a square root relationship, okay? What would you need to know on the AP test? Probably not how to calculate this. Would you have to tell them that you expect hydrogen will move faster than oxygen? Yes, you should be able to do that. I don't think it's likely they're going to ask you to pin down a number like 4 times faster. I mean, they could. I just don't think it's very likely. Now, what if we had flipped them and we got this rate equals 1/4? Well, that would tell you oxygen moves at 1/4 the speed of hydrogen. Now, how do I know that? Because oxygen's heavier, right? I mean, this is the easy concept stuff, right? So oxygen being heavier is going to move 1/4 the speed of hydrogen, or hydrogen being lighter will move 4 times the speed of oxygen. There you go. Now, when I say that, we are holding constant the temperature, because we know temperature is a measure of kinetic energy, and kinetic energy is a measure of mass times velocity squared, because those are on the formula chart. You should know those connections, and we've covered it already. All right, so here's what I see very likely to be the case on the AP exam. A question like I have down below here. I need a little illustration for you. These are called particulate diagrams, because they're diagrams that show particles. I know. Sounds scary and fancy, doesn't it? And it's not. It's kind of a letdown. But there's a strong possibility you might have to draw a particulate diagram on the AP exam. I'm trying to show you it could be as simple as this. Okay? Okay. So I have 2 gases, and I did gas A over here, and then I did gas B over here. And I used my fancy pen thing now in PowerPoint, and I did some really cool little designs. But here's what you need to see. Notice the sizes of those particles are different. So I'm expecting A is a heavier particle because it looks bigger, and B is a lighter particle because it looks smaller. Are you with me? Right? Okay, good. They're at the same temperature, so do they have the same velocity? Well, temperature is a direct measurement of the average kinetic energy. And we know kinetic energy is equal to 1/2 the mass times the velocity squared. So let's analyze this. Same temperature, same average kinetic energy. Like if I was writing an answer on the AP exam, I'd probably write it this way. I would know what AVE means, and I would know what KE means. You might, I mean, for the 1 second, half second longer that it takes to write out the word average, you might write that. Okay, whatever. Same temperature, same average kinetic energy. What do I see of gas A? The mass is larger. What do I see of gas B? The mass is smaller. So what do I know about their velocities? Okay, so check out. So these are next to each other. Remember, we talked in the gas laws, if the variables are next to each other, they're inversely related. If one goes up, the other goes down. Whichever way, okay, one up, one down, it has to work that way if they're next to each other. If they're on the same side of the equation, they have to work that way, all right? So the mass is larger, therefore, we do know what the 3 dots mean. We know it means therefore. Mass is larger, therefore, the velocity, oh, I should very much say average velocity is, if mass is larger, the average velocity is smaller or slower or some word that means that. We're good with synonyms, okay? On the other side, and I would do both parts if they asked me to compare, talk about both parts. If they mention both parts in the question, you mention both parts in the answer. Do you hear me? Oh, okay, I mean, like, I don't want to get mean about it. I want you to give me the points though, and we do not give points if you don't mention both parts, okay? So I'm on your side here, mention both parts. The mass is smaller, therefore the average velocity, and if you said speed instead of velocity, we'd be good with that, no worries. Okay, average velocity is faster. There you go. Now, it is often, when we're talking about gases and particulate diagrams, they might actually want you to kind of show in drawing form, faster and slower. How would we do that? Well, we would do it this way. Slower would mean smaller movement arrows. I don't know where these, I'm just guessing like where these particles are moving. Okay, they move randomly here, there, everywhere. I don't think I've moved anything that way yet. Okay. And then faster would mean larger arrows of movement. Okay, so we're saying like in the same time, this one has moved this distance and these have moved this distance. Okay, so this is particulate diagrams. And this is, yeah, like that one bouncing off the wall, just felt like doing that. This is particulate diagrams, and this is how I completely expect Graham's law to work out on the test. Not that you need to calculate it, but that you need to apply it. You need to apply it in a reasonable manner by discussing how temperature affects kinetic energy, and kinetic energy is affected by mass and velocity. So if there's a change in the molar mass, see where Graham's law appears? If there's a difference in the molar mass, there would be a change in the velocity or the rate of speed. All right, so that's Graham's law. That's what I think you need to know about Graham's law. I'm not going to ask you to calculate that in class. I would absolutely ask you to describe it or draw it like I did in class, but I'm not going to ask you to calculate it. So there's that. Pause if you need to. I'm going to clear it. Okay. Next up, maybe. There we go. Here is an old question that is about Graham's law. And let's see what we can do. A half-mole sample of helium gas and half-mole sample of neon gas is placed separately in two 10-liter rigid containers at 25 degrees Celsius. Now, I don't know if any of those numbers matter yet. Let's keep reading. Each container has a pinhole opening. Which of the gases, helium or neon, will escape faster through the pinhole and why? Okay, yeah, I really don't. I need them to be the same moles, the same volume, the same temperature, so I can make a good comparison. So those numbers are there to tell me that much is true. Now I don't need those numbers anymore. I know I'm same. So what's the only thing that's different? Their molar masses, right? And it asked which will escape faster. Did you hear that dead giveaway? I'm gonna try and go for a darker color here. Let's go green. Escape faster. Oh, that alone, that word alone, kind of. I've heard gases, and I've heard faster, and that makes me think Graham's law. So let me ask you, what do we expect to move faster? Something heavy or something light? Something light. So we look up the masses. Helium is about a 4, okay, on the periodic table, where neon's about a 20. Well, gee, that makes it obvious. Wouldn't helium move faster? So it would escape faster through the pinhole. There you go. Okay. Like done. You just pick whatever choice that is. Now, I do like this. Some things I'm just seeing real quick here at a glance. I see the word average. That's always a good thing to put in your answers when you're talking temperature, because temperature is an average of kinetic energy, which is an average of the velocity. Those are averages, just beware, okay? I'm not saying that that is a clue that that's the right answer. Here we have an average again, but there you go. Now, it did not say either diffusion or effusion, and it doesn't matter, but those are also keywords that are dead giveaway of Graham's law. But what did we decide? We decided helium's faster. So I'm not going to choose that. I'm not going to choose that. It's either A or it's it's both. Okay. Now I'm not going to actually answer. I'll let you figure it out because I know you're smart. You can handle it. Again, we said the lighter one will move faster because we're at the same temperature, the same volume, the same number of moles. Everything else is the same. So it's just a mass and velocity question. So there you go. That's how you would likely see it show up on the AP exam. For me, as I take the AP exam, because I would take it three goes through. First time through, I'm reading every question, and I'm answering the ones I know I can answer right away. this would be one of those. I'd be like, oh, well, neon, okay, helium's faster, this one, and move on. Okay. Second go through, just by the way, is when I know I need to derive an equation. I'll actually show a question about that later. When I know I can do it, but it's going to take me some time. And then the third go through is to, if I have time left over, any question, I have no clue what's going on, I'll try to make an educated guess by crossing out ones I know really can't even be true and try and make a good guess on, okay? You better fill in a circle for every question on the multiple choice part. You better, okay, do it. No reason to leave it blank. Don't leave any blanks. Okay, let's talk about Dalton's law. Dalton's law of partial pressures, it's often called, or you'll often just hear partial pressures. You want to hear the Dalton's part of it. Hey, that's fine. It's all the same. Okay. Here's the thing, super easy. If I want the total pressure in a container, then I add up the individual pressures of the gases, and that's my total pressure. And you're like, well, duh, didn't we know that? Well, okay. We had no real reason to think that's the way it worked until Dalton proved it with experiments and results. Okay, so it is true. We know it's true because of Dalton. So it's an easy formula. Now, you almost never on the AP test would be told gas A has a pressure of 4 atmospheres, gas B has a pressure of 2 atmospheres. What's the total pressure? And you have to bubble in 6 atmospheres. Like, that doesn't happen. Almost all the time, as you're about to see, we use Dalton's law of partial pressure in conjunction with other gas laws. It's a great, let's get started kind of step. But one case where it certainly is useful and necessary would be a situation like I have below. So I wrote this question. It is something I feel could be rather common to see on the AP exam. I even took a little illustration off an old AP exam there so you could see what it might look like. I'm hoping you at some point in time last year in pre-AP collected a gas using water displacement. I know in my class we make some hydrogen and it comes through a tube, and we have an upside down test tube in a container of water, and the bubbles come up and get trapped in the container. It really is a lot like this picture. Well, that didn't work. Okay, this picture is showing right here. It's a lot like that. So a gas is being made here. We don't see it, but we can infer a gas is being made here, and it's going through this tube, and they do show me bubbles coming up through what used to be water in that tube, and then it's just collecting here. And we say foolish things like, this allows us, since it's full of water before, and then we're bubbling the gas and it pushes the water out of the way, it's full of pure gas. Well, that's not really truth, because there's this thing about water. It evaporates. So while the gas is bubbling up, some of the water is evaporating too. I don't want to do gas laws thinking I have a pure gas there if it's gas and water vapor. So I need to account for that. So this is a very common way we account for that. Student collects some hydrogen created during the lab by water displacement. She finds the pressure in the container, so the total pressure over here, up here, okay, is 750 millimeters of mercury. What is the pressure of the dry gas alone? Okay, because I want to like do other experiments with the gas. I don't want water vapor in there in my calculations at all. So I'm going to, come on, thank you. I'm going to use Dalton's law of partial pressure here. But here I know the pressure total equals the pressure of the gas, the dry gas, we often refer to it as the dry gas, and the pressure of the water vapor. Now my pressure total, the problem told me was 750 millimeters of mercury. Sorry, I'm in the energy wavelength frequency unit in my other class, and nanometers is now stuck in my head for a good 2 more weeks. So it's millimeters of mercury here. All right. The gas is, I don't know. That's what I'm looking for. What what is the pressure of the dry gas alone. And then the pressure of the water vapor, they do have to give this to you. There's no way to know. You'd otherwise have to memorize a chart. And on the new test, there is no reason to be memorizing charts. Okay, so they told me it's 15.2 millimeters of mercury. I'm going to solve for X. So pressure of the gas, which is X, is, and so yeah, you can see the math is really easy. So Dalton's law is really easy math. Knowing when to use it and how to use it well, that could be tricky. I have another example coming up to show you that it can appear tricky. It doesn't have to be. But anyway, I'm doing this math. Hopefully you're doing it too. The pressure of the dry gas alone, I got 734.8 millimeters of mercury. So there's my final answer. That would be something that would be rather common to see on the AP exam. They could easily ask that kind of question. I haven't seen this sort of thing often, but it is a possibility. Okay. Now, as I said, I have another example. Maybe. I thought I did. There we go. Okay, so here's one also that I took from the AP exam. It's just a picture. Now, it had an actual question with it, but I want to just discuss this picture with you because this picture illustrates Dalton's law of partial pressures. So we have a container, and it looks like it's split in exactly half. So the volume is the same on each side. So I'm going to like mark that down over here. I'm going to make just a little less. Here's constants. Volume must be constant. Same volume here, same volume here. Okay. Temperature would be constant because whatever the temperature is here, I have no reason to doubt that the heat or the lack of heat would spread from one container to the other, and they would even out and be at the same temperature. Okay. What about the moles? Because I'm just kind of going through my PV equals nRT stuff. We know R is a constant. Okay, so I'm not going to mention that anymore. But volume is a constant, temperature is a constant. What about moles? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 grays. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so moles is constant. That's why they like particulate diagrams. It's as easy as that to like determine relative things. Are they the same or are they different? If volume's constant and temperature is constant and moles is constant and obviously R is constant, yeah, pressure would be constant too, would be the same in both. So I expect whatever the pressure of the, I'm going to call it gray is, and whatever the pressure of the white is, that they are equal. Okay. Then we remove the barrier. And now look at this. So what has changed? The volume has changed. Okay, if volume changes, I still have 14. Let's do another constants list here. I still have 14 grays and 14 whites. So N is the same. I'm going to assume they mix slowly enough that the temperature stays the same. But now the volume has gone up. So what do we expect? We expect the pressure to go down. Okay. However, we're also mixing them together. So this is now a Dalton's law thing. The pressure total will equal the pressure of the gray plus the pressure of the white. However, I expect their pressures now to be half because it looks like it doubled. Because remember, these were the same volume. I expect it to be half the pressures they were over here. Do you see how this thought experiment works? We could still, if we got some numbers now, we could still find the new pressure. I would just need to know some numbers for either the old pressures, or I would need to know the new pressure and I could divide it and calculate what the old pressures were, one way or the other. So that's Dalton's law. We can add gases into the same container and the pressures just add up, one after another, after another, after another, okay? Or if I know the total, I can subtract out the pieces that I do know and find a piece I don't know. We can go either way, okay? I'm gonna clear the drawings. And something else to consider with Dalton's law, mole fraction. This occurs on the AP test quite often, like a lot. Not necessarily difficult, but you have to know what the heck's going on. Plus, mole fraction is a formula on your formula chart. By the way, the symbol for mole fraction is, let me get some color here, I'll go paint this on, is X. Okay, like officially. I think it's actually the Greek letter chi, which is a fancy looking X. The same kind of X for Christmas. We shorten Christmas to, people think it's Xmas. No, it's chimus. That's the Greek letter chi, which is the first letter of the word Christ in Greek. So we're still saying Christmas. We're just shortening with the first letter. I mean, anyway, moving on. So X, fancy X. Okay, Greek letter chi is mole fraction. What is mole fraction? It's what it sounds like. It's the fraction of moles. It's the moles of whatever gas you're worried about divided by the moles of all the gases in total. And we do not multiply by 100. We leave it as a decimal. We like often having two digits after the decimal. 0.92, 0.04, 0.68. Okay. So how would we employ mole fraction and Dalton's law together? This is asked often. It's not hard. You just have to know what's going on. Here's a question very similar to ones I've seen on the AP exam before. I changed some identities to protect the innocent, you know, one of those sorts of things. Anyway, a gas mixture at 0 degrees Celsius and 1 atmosphere contains 1 mole of neon, 1.5 moles of xenon, and 2.5 moles of oxygen. What's the partial pressure of neon? Okay. Partial pressure of, okay, so I need to know pressure total to find partial pressure of neon plus partial pressure of xenon plus partial pressure of oxygen, and I do have pressure totals 1 atmosphere, and yeah, that's why you don't do it this way. Okay, we don't have enough information to do it this way, but doing it with mole fractions, we have plenty of information for. Check out how easy this is. I'm looking for partial pressure of neon, so let's find the mole fraction of neon. Neon, we were told, was 1 mole out of a total of 1 plus 1.5 plus 2.5 is 5. So I have 0.20 mole fraction of, we don't put a label on it. It's weird, I know. 0.20 is our mole fraction of neon. Well, that's the fraction of moles of neon that would be the same as the fraction of pressure of neon. It's all ratio, okay? So this ratio would be the same as that. So I'm gonna take 1 atmosphere of total pressure. I'm gonna multiply it by 0.20 mole fraction for neon, and I see, oh, the pressure of neon is 0.20 atmospheres. There we go. There's my answer. That wasn't hard, but I had to know what the heck was going on. So that's why mole fraction often comes into play when we're dealing with Graham's law, because we don't know the pressures, but we do know the moles. And so if I use that mole fraction and the total pressure, then we can totally do the work super easy right there. And in fact, we could do the mole, we could do it for all of them. I would take 1 atmosphere times the mole fraction of xenon, which is 1.5 out of 5. That's not going to be fun, but that's what it would. And then 1 atmosphere times, I don't know why I have an extra decimal there, 2.5 out of 5, and that'd be the mole fraction of oxygen, and I could do that. Now, when I'm done, I should see all those pressures add up to be 1 again, if I were to do that. Question did not ask for them all, so I'm not going to spend any time doing them all, but that's the way that works. So if you've never seen mole fraction before, it's this easy. It's a fraction of moles, and we could absolutely use it to ratio to find the partial pressure of something if I know the total. It works really well because of Dalton's law. So there we go. Okay, I'm going to clear this away. No, I want to clear. There we go. Okay. Brain fart moment there. I want to discuss gas density with you. Okay, remember when I said that I would take the AP exam in 3 passes? First pass, I'm reading all questions. I'm answering the ones I know I can do right away, like immediately. That's not going to be this one. But they do kind of often ask about densities of gases on the AP exam. So that is something that is really going to be good for us to be able to figure out. Okay, so density is mass divided by volume. By the way, that formula is on the formula chart. So you don't need to memorize it, it's there for you. And it's even there in the gases section. So do I believe it's very likely they're going to ask you about density of gases and not about solids or liquids? Yes, I do find that very likely. It is there, and it applies to solids and liquids, but it's there in the gases section. So it's most likely, I'm trying to wink at you, you know, it's probably going to be used as a gas thing. Okay. I've got 3, it says 3, they're identical rigid containers under these conditions. And I'm looking for the density of the gas. Oh, and which one's greatest? Well, I can see the temperature is the same. Well, that's great. But all I have to go with is molar mass and pressure. And the pressure's even changed and the molar mass has definitely changed. So I'm not really sure what to do. Well, we have to do some work. I need to get mass divided by volume to find density, to figure out which one has the greatest density. If I start with PV equals nRT, you'll notice I do have the V for volume in that equation, but I don't have the mass anywhere in that equation. But I do have moles in this equation. And I know that moles is gram, wow, I know that, I'm about to say this wrong, my bad. I know that molar mass is grams per mole. Okay, so that's a capital M for molar mass. Molar mass is grams per mole. So let me rearrange. Moles then must be grams divided by molar mass. So now I can stick that up there. Wow, that was a sad arrow. Let me try that again. There we go. I can stick that up in there. So pressure times volume is now grams divided by molar mass times R and T. And mass is grams. Oh, that's good. Volume is volume. Ooh, that's good, except I want the grams on top of volume. So I'm going to divide both sides here by volume. See how I now have grams over volume? Plus, I want to get rid of this random M in a minute, but I'll get to that. Okay, so right now I have pressure is grams divided by volume. I need a longer line. RTM. And then this I'm going to call density, because that's what density is. Didn't we just say mass is grams and volume is volume? So I have pressure equals density times RT over M. Now I want to get density by itself. So the density is pressure times the molar mass divided by R and T. Ooh, I now have an equation for density, and that's what I was looking for. And I know R is a constant, so I'm really not going to worry about that. Ooh, check it out. Temperature is constant. It tells me it's the same, so I'm not really going to worry about that. So what would really make for the density to be greater or not as great? The pressure times the molar mass. Oh, I can do that. I have that data, don't I? Check this out. Let me get to a darker color here. Here we go. I can take the molar mass times the pressure. I can take the molar mass times the pressure. I can take the, ooh, I can achieve this. That's why I would save this for my second go through. I would read that going, oh, I know how to do this. I know how to get density worked into my ideal gas law equation. However, it's going to take me a minute to do that. So I wouldn't do it right away. I would come back to it later. Okay, so 16 times 2, that's a density of 32, divided by RT, whatever that is. I'm not going to worry about that at the moment, okay? Relative density of 32. 30 times 4, well, I'm glad they gave me some nice numbers to multiply there, 120. Certainly, this is obviously greater than that. That's all I really care about. Now, it's not the real density. It would be divided by R and T, but I don't need to worry about that. There's no numbers in the answers. Okay. And then 58 times 2, oh my goodness, I think that's 116 though. It's not the same as 60 times 2. So there we go. So that's even greater than that. Oh, I found the greatest. So there we go. So this illustrates something that they do ask kind of often. They ask about density when it is in conjunction with gases. Sometimes it's just a thought experiment, and sometimes like this question, you totally need to just find the equation. And this equation, this one I ended up with here, that density is equal to PM over, RT, good luck, pirate. That equation is not on your formula chart. The density, the density part is, the moles is grams divided by molar mass part is, the ideal gas law is, those three are on your formula chart, but putting it all together into one, not on your formula chart. So I wanted to show you this so you could be ready to do that. Okay, let's clear this away. Believe it or not, we are actually almost done. One final thing I wanted to go over with you, some gas stoichiometry. It is not uncommon for them to ask you to do stoichiometry with gases. And you can do stoichiometry with gases like you do anything else, because gases have moles, and gases have volumes, and gases have pressure. And you can do stoichiometry with all that. But something that very often comes up as like a part A or B or something, like something for one quick, fast, easy point, especially on the free response portion, is that using this identity. 1 mole of any gas at STP is 22.4 liters. Now this is on your formula chart. So imagine I had a container. I'm going to draw a sad looking box here. Here's my sad looking box. Okay. And this box had a volume of 22.4 liters. When that's full of a gas, I have 1 mole of gas in that box. This only works for gases. Must be a gas. Doesn't work for a liquid. If I fill that with a liquid, I likely have a lot more moles of a gas, or than a gas. Okay. Put in perspective, a mole of water is going to be about 18 milliliters, not even close to 22.4 liters. Okay, so this only works for gas, and it only works if we're at STP, standard temperature and pressure. So here's where I put like big symbol of asterisk, like warning, watch out, careful, when can we use this? When you're working with gases and we're at standard temperature and pressure, STP. What are standard temperature pressure? You should know, but hey, it's on the formula chart. So if you have a brain fart that day, no worries. It's on your formula chart, 273.15 kelvins and 1 atmosphere, which we also know, it's listed on the formula chart as 1 atmosphere. We also know that's 760 millimeters of mercury, that's 760 torr, etc. Okay. This is an old test question that I feel is very indicative of this kind of question. Calculate the number, I'm jumping down here, by the way, sorry, jumping to the final question. Calculate the number of liters of hydrogen fluoride gas, okay, gas, they're telling me it's a gas, measured at 23 Kelvin, and when I see a standard temperature and a standard pressure. I'm already thinking 22.4. Let's see if I need it. What will calculate the number of liters that will be consumed if all the H3BO3 reacts. Okay, yes. I'm betting I'm going to use 22.4 liters. But I need to start with my boric acid, my H3BO3. Okay, what do I know about the HB molar mass? Okay, so tetrafluoroboric acid is a strong acid with the formula of that. The acid is prepared by reacting weak acid, boric acid, molar mass with hydrogen fluoride according to the equation above. Okay. Now, unfortunately, I cut out part A or 1 or something that had the mass, but that doesn't matter. Let's pick a number, 38 grams. I have 38 grams of boric acid. And I want to know how many liters of HF I would need to react completely with that 38 grams. Okay, well, they give me a molar mass. That was nice of them. They actually do that a lot. It's a time thing. They know you're in a rush because it's a time test. So they'll often give you a molar mass, or it might be something that you can do like HF. I'm like, add 1 to, you just add it up on the periodic table super fast and you're okay. All right, so grams to grams, moles to moles. This is my mole ratio. 1 mole of H3, well, that's supposed to be an H3BO3. I know, you wish my writing was as fancy as the rest of my print here, I know. Makes 4 moles, or needs 4 moles of HF to react. But they didn't ask for moles, they asked for liters, so 1 mole of this gas at STP. Now I've checked that it's a gas and I've checked that it's at STP. Those check out, check, check. Both have to be true. I can do 22.4 liters there. And then there's my work. Grams is canceling grams, moles of that, cancels moles of that, cancel liters is my answer. There you go. So that is how they often do gas stoichiometry. Quite often, especially in the multiple choice, but quite often, even on the free response, it is at STP. What would I do if it's not at STP? I would not do this. I can't do that if it's not at STP. I can't. And I can't do it if it's not a gas, but I can't do it if it's not an STP. What would I do? I'd have to stop my railroad track here, find the moles of HF, and once I know the moles of HF, I would use PV equals nRT. I would plug in the moles there, and I would solve for the X there. So I'd put in whatever the pressure they told me was, I'd put in whatever the temperature they told me was, if it wasn't at STP, and then R's off to form the chart. And I solve for volume, and I get my liters. It would work just fine. What if you mess up and you don't remember it's 22.4 liters and you do it this way anyway? You'd come up with the same answer as if it was STP. So it works either way. Ideal gas law always, always, always works. 1 mole is 22.4 liters. I said to erase it. I wanted my eraser. There we go. 22.4 liters is 1 mole, only works for gases at STP. Ideal gas law works all pressures, all temperatures. 1 mole is 22.4 liters, only works at STP. Be very careful, you only apply it when necessary. If anything, default to not being at STP and working it with the ideal gas law, and even if you were at STP, it's okay, you get the correct answer regardless. So there you go. Okay, so that's what I wanted to wrap up today with. We actually have still some more to talk about. We need to talk about non-ideal gases. And you're like, oh no, actually it's not that hard. But that's also something that they ask a lot on the test. And it is kind of easy. If you remember what makes a gas ideal, then the opposite makes it not ideal. It will be that easy. I'll give you some example problems. We'll work through those later as well. But that's next time. There's some practice for you going on in Canvas. I hope that this has sunk in. A lot of this is mental. Okay, there's some calculations with the stoichiometry. I won't deny that. Okay, there is that. There is No, I wanted to go back. Okay, I should clear this too. I'm sorry. Let me clear all this away. I wanted to review, and I don't think I'm going to be able to do this well. Oh, there we go. Okay. A lot of this is mental, but there's calculations with gas stoichiometry. Every once in a while, there is a density question. I didn't even have to actually like calculate the density, but I had to derive the equation for this. I'm sorry, it's going to happen. Now you've seen it happen, so you know how to do it if you need to do it on the test this year. You've seen it once. Okay. Mole fraction, super easy, probably why it's on there all the time. You just have to recognize, again, it's a mental thing. You have to recognize, oh, I can't use pressures to add up for the total, but I can use mole fractions instead to add up to the total. That would work, and it absolutely will work. We talked about this thought experiment. Be ready for particulate diagrams when it comes to gases. That doesn't make it a hard question. In my opinion, it usually makes it an easier question. So be ready for it. They like particulate diagrams with gases, just expect them. Collecting gas with water displacement, we have to count for that water, okay? Very common use of Dalton's law is to do that, especially in laboratory. I wish we weren't virtual, and I wish we could do a lab together. I do have a lab where we collect the gas with water displacement, and we subtract out the water and do the rest of the math with the dry gas alone. Good use of Dalton's law. And then we talked about Graham's law, and like, look, Graham's law is mental. I would completely expect it to look like I showed you with the particulate diagrams, where you just compare if the molar mass is going up, its speed's got to be going down. So if it's heavier, it's slower. If it's lighter, it's faster. Mental only. Maybe you'll need to draw that. And I showed you how just, you can add some correctly sized arrows. Okay. I cannot imagine you'd have to actually calculate this formula with the square root and all that, since it's not on the formula chart. Now, not that it'd be hard, but I don't think they're going to do that. They're going to ask you to use it in other ways, like we did. Okay. So that's it for our gas laws work today. I hope this helps you understand some more of the little details. Sorry there's so many details with gas laws, but there's so many details with gas laws. It's just the way it is. I hope you kind of realize it all centers on that ideal gas law equation. And so when in doubt, we start there and we work from there. Good luck on your practice in Canvas. I'll see you around next time.